You know that feeling, right? We've just unboxed something incredibly powerful, maybe a new supercomputer, or perhaps a really high-end audio mixer for your studio setup.
Oh, yeah. The
Huh.
excitement is huge.
Totally palpable. But then, there it is, that stack of documentation, maybe thicker than an old phone book.
Mm-hmm. Sitting there like a challenge.
Exactly. It's like the gatekeeper to all that amazing potential, and honestly, it can feel like this huge mountain you have to climb before you even think about plugging anything in.
It's that classic moment, isn't it? That initial thrill hits well, maybe the quiet dread of, okay, now what? This thing can do incredible stuff,
Right.
but getting to those capabilities, making it really perform, that takes understanding. It's a bit of a knowledge barrier, yeah.
Yeah.
But it's also, an invitation to really get what's going on under the hood.
And that's exactly the journey we're starting today. We're not just flicking through a manual. We're taking a proper deep dive into the user guide for a really sophisticated piece of kit, the RNS FSPM from Rohde & Schwarz. Our mission, basically, is to take this super technical guide, the kind usually just for engineers, right, and distill it. Make it understandable, maybe even surprising, and definitely actionable for you, our listener.
Right.
We're going to explore how a highly precise instrument like this actually comes to life. From the moment you get it out of the box, the physical setup, all the way to its advanced capabilities, and even how it talks to the wider world.
Think of it less like a dry technical reading, more like a guided expedition. We'll go way beyond just here's how you plug it in.
Yeah.
We want to uncover the thinking behind its design, those layers of interaction between human and machine, and the mind-boggling precision it offers.
Sort of a behind-the-scenes look.
Exactly. A
Yeah.
behind-the-scenes look at what makes a technological workhorse like this tick, and what the creators really prioritize when they design something so critical. We're hoping to dig out some hidden insights from what might seem like just, standard instructions.
Okay, so the adventure kicks off the second the RNS FSPN arrives. This isn't just any old package. It's a meticulously crafted scientific instrument.
Mm-hmm.
And right from that unboxing moment, the manual pulls you into this world where every single detail, even just how heavy it is, tells you something about its purpose and the engineering behind it. So imagine this scenario. Your brand new RNS FSPN has just been delivered. You see the box. You feel that buzz of anticipation.
Yeah.
And then the manual hits you with this really critical piece of info about its sheer physicality. This is not some lightweight gadget you can just sling around.
Oh, definitely not.
It specifically warns that a single person can only safely carry, I think it's a maximum of 18 kilograms. And even that depends on your physical condition.
Yeah, and that 18-kilo figure, it's not just a number, is it? It's like a design philosophy made physical,
Yeah.
dense.
Right.
It immediately tells you the manufacturer is serious about robust, high-quality internals, things designed for extreme precision, probably good shielding from interference, thermal stability, all that stuff.
So it's not meant to be portable, really.
Not in the usual sense, no. It's more like a stable, almost immovable lab fixture. It's built for, uncompromising performance.
Yeah.
And its weight is the very first undeniable clue about what it's for and how it's built.
That straightaway gives you a sense of the care required, doesn't it?
Yeah.
And that leads right into what the manual calls the unboxing ritual.
Ritual. I like that.
Yeah, and it sounds like it's way more critical here than, say, unboxing a new phone. The very first steps are absolutely paramount. You have to carefully unpack the FSPN, and importantly, it advises you to keep the original packaging.
Yes, the packaging. Always keep the packaging for something like this.
It's not just for, recycling. It's explicitly for future transport or shipping.
Right. Very practical.
And then you're meticulously checking everything against the delivery notes. Is it all there? And inspecting for any damage whatsoever.
That initial ritual, as you called it, it's so crucial for any high-value precision tech. It's like establishing a perfect starting point, a baseline. If something is missing or if you see any damage, the instruction is clear. Contact Rohde & Schwarz immediately.
Right. Don't even try to power it on.
Exactly.
Yeah.
Because the integrity of that instrument, even before you give it power, is absolutely vital for its performance, its accuracy, its lifespan. Any little defect could potentially impact those hyper-accurate measurements it's designed for.
Or worse.
Or worse, pose a safety risk down the line. It's really about protecting your investment, ensuring it works optimally right from day one. It kind of highlights that the life of this instrument starts way before you actually flick the switch.
Okay, so it's safely out of the box. Now, you can't just, shove it onto any old bench space. Choosing the operating site for the FSPN is apparently much more involved.
The manual's very specific here.
First thing, indoor use only. This is definitely not your rugged, take-it-anywhere field gear.
And they are really quite emphatic about that, aren't they? The casing is explicitly stated as not waterproof.
Which sounds serious.
It is. It's not just a suggestion, it's a critical safety warning. If water gets in, it could electrically connect the casing to live internal parts. That could lead to electric shock, serious injury, or, even worse.
Wow.
It's a stark reminder that precision electronics, they often have these inherent vulnerabilities when you take them out of controlled environments. Like, you wouldn't leave a delicate scientific microscope out in the rain, right?
No.
This instrument needs a protected, predictable setting, both for safety and for its long-term accuracy.
Okay, beyond water, there are other specific environmental things. Like it operates up to 2,000 meters above sea level.
Though higher might be possible, check the docs.
And it's designed for pollution degree 2 environments. What does that mean?
Pollution degree 2. Okay, so these environmental factors, they directly impact how well it works. Altitude, for instance, affects air density, right? Which affects cooling. Thinner air means less natural cooling. And pollution degree 2, that's basically a safety classification. It means it's built for places like a typical lab or an office. You might get some non-conductive dust, maybe you spill coffee nearby and it doesn't conduct.
Right.
But it's not designed for, say, a heavy industrial factory floor with conductive metal dust or abrasive particles or maybe corrosive fumes floating around.
So fairly clean conditions needed.
Exactly. It's robust, but within defined clean conditions. That's crucial for keeping its delicate internal circuitry happy and maintaining that precision over time.
And this is where it gets really interesting, I think, regarding where you put it. Preventing overheating. It's not just about the surface, but how it breathes.
Yeah, airflow is critical.
The manual mandates a minimum 10-centimeter distance between the fan openings and anything nearby to make sure there's enough airflow. And you definitely should not place it next to other things that generate heat, like radiators, obviously, or even just other equipment that gets warm.
Overheating is like the silent killer for these precision instruments. Too much heat can cause components to drift out of calibration.
Ah, okay.
It could degrade performance or even cause permanent damage. Think about a high-performance gaming PC that overheats and slows down. This is way, way more sensitive.
Right.
So keeping that proper ventilation isn't just about making it last longer. It's about making sure the instrument can maintain its specified accuracy, maybe over hours or days of operation. It really speaks to the detailed thermal design that goes into this kind of equipment. Even a few degrees can subtly mess with the measurement integrity.
Stability is also huge. It has to be placed on a stable, flat, and level surface with the bottom facing down. Pretty clear.
Yep, no wobbles allowed.
And if it is designed for other positions, it has to be secured properly to stop it from falling over.
Makes sense, given the weight.
And if you're rack mounting it, putting it into a big system, you need a specific rack adapter kit. The order number is in the spec stock. But even more critically, it says you need an efficient ventilation concept for the rack itself to stop it overheating inside an enclosed rack.
Right, because sticking it in a closed box changes everything for airflow. So all these environmental things, the setup considerations, they're crucial because they directly impact accuracy, longevity, and, of course, safety.
How so, exactly?
Well, a precision instrument is essentially a finely tuned measuring device, right? So any mechanical instability, even tiny vibrations or temperature swings, or maybe electromagnetic interference from nearby gear, all that can introduce errors into the measurements. It degrades the very accuracy you paid for.
Like trying to measure something with a shaky ruler.
Exactly. Or like a high-performance race car, you wouldn't just park it anywhere, would you? You'd put it in a controlled environment to keep it performing optimally. For complex electronics, a stable, controlled environment minimizes internal stresses, ensures things stay at the right temperature, and helps maintain the integrity of those delicate circuits over thousands of hours. It's really a testament to the engineering that every little detail, even the air around it, the surface it's on, contributes to how well it performs.
Okay, so it's physically in place, stable, ventilated. The next big step is connecting power. And here, safety is absolutely paramount. The manual details that the FSPN is an overvoltage Category 2 product.
Overvoltage Category 2.
Yeah.
Okay. That essentially means it's designed for connection to the kind of fixed electrical installation you'd find in, say, a typical building, like for household appliances or general office equipment.
So not for plugging directly into some heavy industrial mainline.
Exactly. It's built to handle the usual transient overvoltages you might get on those circuits, like from switching big motors or something. But it's not meant for, the main distribution panel or super heavy industrial loads. It just tells you the right kind of power environment it expects and the level of protection it has built in.
Got it. Beyond that category, there are some really crucial safety measures you have to follow before you even think about flipping the switch.
Non-negotiable stuff, really.
You must ensure the product's indicated voltage and frequency, usually on a label somewhere, match the power source you're plugging into.
Check. Check and double check that.
And you're explicitly told, only use the country-specific supplied power cable. You can't just grab any old cord.
No, definitely not. That specific cable is important.
It has to be the one delivered with it, and it always must plug into an outlet with a protective conductor terminal, meaning it needs a proper ground connection.
These are absolutely fundamental electrical safety practices, but they're amplified for a high-value device like this.
Huh.
Using the right cable ensures proper grounding. That's your main defense against electric shock.
Okay.
It also guarantees the cable can handle the current safely, preventing overheating or, fire risk. Checking the voltage and frequency stops you from frying the instrument's internal power supply right away.
So it's protecting the instrument and the user.
Exactly. Both. These are totally non-negotiable steps for operating it safely.
And finally, a really basic point, but one that's easy to overlook. Regularly check the power cables for any signs of damage.
Fraying, cucks.
And route them carefully so people don't trip over them. Sounds simple, right?
Yeah.
But a damaged cable is a serious electrical hazard, potentially exposing live wires.
Yeah.
And tripping over the cord could send this expensive, heavy instrument crashing to the floor. Catastrophic damage.
Yeah, you don't want that. And the manual even goes further. It unpacks those universal safety symbols you'll find printed right on the instrument itself.
Oh, yeah. Like what?
Well, there's the read product documentation symbol. Looks like an open book.
Yeah.
Basically saying, hey, potential hazard here, read the manual. A good reminder those pages are vital.
Okay.
Then the heavy product symbol, usually a weight icon. A clear warning. Be careful lifting this thing.
Right.
You'll see the electrical hazard symbol, often a lightning bolt, warning you about live parts inside, risk of shock, fire, injury, even death. Very serious.
Definitely.
And finally, the hot surface symbol, maybe like wavy lines rising, indicates a risk of burns or fire, often near the vents where hot air comes out.
So these little pictures are crucial warnings.
Exactly. Each one is a concise, universal warning. Instant visual cues about potential dangers right there on the device.
So what's the big takeaway here? This whole first section, it really underscores a vital principle, doesn't it? Setting up a high-precision instrument isn't just about getting it working.
Not at all.
It's fundamentally about safety. Protecting you, the user, and protecting the device itself. Every warning, every specific instruction about placement or power, it's all there to ensure reliable, accurate operation and to prevent costly damage or, much more importantly, someone getting hurt.
It's really a testament to the meticulous engineering, isn't it? They think not just about building the device, but ensuring it can be deployed safely out there in the real world. In this kind of high-tech precision environment, that user manual becomes a critical safety guide, almost like a silent guardian for the tech and the person using it.
Okay, so the RNS FSPN is safely unpacked, perfectly positioned, power connected correctly. Let's talk about bringing it to life and how you actually, interact with this powerful thing.
Right, the human-machine interface.
The manual gives a clear overview of its power states, which are indicated by the color of an LED. Off is a gray LED, and the power key is set to 0.
Okay.
Standby shows an orange LED, and the main power switch on the back is set to I. And ready is a green LED, also with the main switch at I.
Those distinct states are pretty common in complex electronics, aren't they? Gives you immediate visual feedback on what the instrument's doing.
Yeah, it's not just on or off.
Right. A standby often allows for quicker boot-up times, for instance. Or maybe it maintains critical internal settings without drawing full power so it can get back to full operation faster when you need it.
And switching it on and off isn't just, pressing one button. It's a two-step process. First, you flick the main power switch on the rear panel.
The main breaker.
Then you press the standby key on the front panel. For a full shutdown, you press and hold that standby key until the LED turns off, and then you physically disconnect the AC power cable.
That specific sequence is important.
Why is that?
Well, that controlled shutdown sequence is crucial. Just pulling the plug directly, especially on something running an operating system like Windows. That could lead to corrupted data, messy software shutdowns, maybe even damage to internal components if things are mid-write. It's all about protecting the instrument's integrity, making sure it shuts down cleanly, preserves its calibration, its configuration data, ready for the next time you power it up.
Okay, now here's where it gets really interesting in terms of modern lab setups.
Okay.
Connectivity. The RNS FSPN can be hooked up to a local area network, a LAN,
Right, Ethernet connection.
which enables remote operation, transferring data, accessing measurements from a different computer. This seems like a potential game changer for a lot of labs, doesn't it? Allowing automated testing, maybe centralized control.
Oh, absolutely. It's all about efficiency and flexibility. Imagine a test scenario where the instrument has to be inside a shielded room, maybe an anechoic chamber.
Right, you can't be in there with it.
Or you need to run measurements for days, unattended. LAN connectivity makes that feasible, lets you integrate the FSPN into a bigger test and measurement system, or even just lets a team collaborate on the data from different workstations.
But, and this is a big but, the manual throws in a significant curveball here. One you don't often see flagged quite so prominently in a typical user guide.
Oh, what's that?
A really clear security risk alert. It actually says, quote, when connected to the LAN, the product may potentially be accessed from the internet, which may be a security risk.
Wow, okay, that's direct.
It gets better. It warns that attackers could misuse or damage the product. This feels like astonishing transparency for a user manual.
That is fascinating and incredibly important.
It even goes so far as recommending a specific Roden-Schwartz white paper on Windows 10 malware protection.
That level of direct security warning is really something. It absolutely reflects this growing awareness by manufacturers that their instruments, they aren't just isolated lab tools anymore, they're network devices.
Because it runs Windows.
Exactly. By running on Windows, the FSPN basically inherits the vulnerabilities of a general-purpose computer. The manual isn't just giving instructions here, it's providing a really responsible, ethical warning. They're telling you, the user, look, this connectivity is powerful, but hey, it opens up a new way for bad actors to potentially get in. That wasn't really a concern a decade ago for lab instruments.
True.
And recommending a white paper on malware protection? That's really going the extra mile. It shows a serious commitment to secure operation in our connected world. It's proactive. It acknowledges that the instrument's integrity isn't just about the hardware, but its digital environment too. It's a stark reminder. Even a precision measurement device is now an IT asset, and potentially a security concern.
And it doesn't stop there with the network warnings. There's a crucial warning to consult your network administrator before connecting or configuring any network settings.
Ah, the IT department call.
Yeah, because it says errors can affect the entire network. This isn't just a polite suggestion. It sounds like critical advice for keeping the whole network stable.
Absolutely. Misconfigured IP addresses, wrong subnet masks, other network settings.
Yeah.
They can cause conflicts, take down network segments, maybe even disrupt an entire company network if you're not careful. For a highly technical instrument like this, you can't just assume it's plug and play like your home router.
Yeah.
It needs proper integration. And that often means involving the IT folks who understand the bigger network picture, who can assign IP addresses correctly, set up firewall rules if needed. It really highlights how modern labs are becoming more interdisciplinary, bridging that gap between engineering and IT.
Okay, so moving beyond the physical connections, let's talk about the brain of the FSPN and how you actually navigate it. What's fascinating, as you mentioned, is that this high-precision measurement instrument actually runs on a very familiar operating system, Windows. You can apparently even access the Windows environment directly just by pressing the Windows key on an external keyboard.
That's a really significant design choice, isn't it? Running on Windows gives it that familiar graphical user interface, which makes it instantly more accessible to anyone comfortable with a PC. It also implies a certain level of computational power and flexibility you might not find in older, traditional embedded systems. It means you can do advanced file management, maybe install compatible software utilities, leverage standard IT tools right there on the instrument itself. It really blurs the lines between a dedicated instrument and a highly specialized computer.
And it's not just locked into English either. The system supports various keyboard languages. German, Swiss German, French, Russian, which you can configure through the standard Windows settings.
Now, that might seem like a small detail, supporting different keyboard layouts like German or French or Russian, but it actually reveals quite a bit about the design philosophy. It's not just localization. It shows a real commitment to making these high-tech tools genuinely accessible globally. It acknowledges that ease of use isn't just about the main interface, but every little interaction point matters for a diverse international user base. It just makes it more efficient and comfortable for users everywhere.
Now, here's a really critical security detail: user accounts and passwords. Some admin tasks, like setting up auto login or configuring the LAN settings, need administrator rights.
Standard practice for protected settings.
But what's fascinating, and maybe a bit alarming, honestly, is that the initial password for all the default user accounts is 894129.
Oh dear. A fixed default password.
Yes. And the manual strongly recommends changing it immediately because, quote, it's very weak.
That highlights a really common yet severe vulnerability you find in the default setups of so many network devices. Industrial controllers, home IoT gadgets, you name it.
Right.
Providing a default password makes initial setup easier, sure, but leaving it unchanged, that's a massive security hole. 894129 is easily guessable, or it's probably listed online somewhere. It makes the instrument a prime target for unauthorized access, especially if it's on a network.
So change it immediately.
Absolutely. That strong recommendation is critical advice for anyone using this system. It really underscores that the first step to securing your expensive instrument isn't some complex firewall configuration. It's just basic password hygiene, a fundamental security lesson for any connected device, really.
It also mentions that if you do use auto login, changing the password means you have to adapt the auto login settings first. Adds a little complexity, but necessary.
Right, you need to update the credentials the system uses to log itself in.
And for users who need a bigger picture, you can connect external displays using either DVI or DisplayPort connectors on the back panel, which could effectively turn the instrument into a proper workstation, couldn't it?
Oh yeah, connecting external monitors is a huge ergonomic win.
Yeah.
And practical too, especially if you're doing detailed analysis, looking at multiple channels at once, or maybe collaborating with colleagues. It means you're not stuck squinting at a smaller built-in screen. You get more space for data visualization, maybe even multitasking with other analysis software on the same display setup. It's all about enhancing the user's workspace for tackling complex data.
Let's take a quick tour of the physical interface now, the actual keys, knobs, and connectors that bring this digital brain to life, starting with the front panel.
Okay, the hands-on stuff.
You've got your standard alphanumeric keys and a dedicated keypad. For entering data, selecting units like, hertz for hertz or dB for decibels, pretty standard.
Yeah.
But the real star, often for making precise adjustments, is that rotary knob.
Ah, the rotary knob, often the unsung hero of instrument control, I think.
Why is that?
Well, its ability to finely tune parameters or quickly scroll through long lists, combined with that tactile push-to-enter function. It provides a really intuitive and efficient way to make precision adjustments, sometimes much better than just using a mouse or a touchscreen, especially when you need to make tiny incremental changes.
Yeah, I can see that.
And the fact that they include Undornado functionality right there in that control area, that's a fantastic quality of life feature. It significantly reduces that fear of accidentally messing up settings during a critical measurement.
You also have your standard ESC key, closes dialog boxes, quits edit mode, cancels data entry, backspace, deletes characters, just like a normal keyboard.
Familiar controls. Good.
Now, on to the really critical measurement connection, the RF input. It's specified as 50 ohm.
Right, 50 ohms. If that number sounds familiar to anyone working with radio frequencies, it's because it's the universal standard impedance for RF equipment.
Why 50 ohms specifically?
Well, it's a historical compromise, really, balancing power handling and signal loss in coaxial cables. But think of it like a perfectly matched highway for your high-frequency signals. That 50-ohm impedance ensures maximum power transfer from whatever you're testing your device under test, or DUT, into the instrument, with minimal signal reflecting back.
Reflections are bad.
Very bad. If that highway isn't perfectly matched, if the impedance is off, you lose signal quality. Some of your signal power literally bounces back instead of going into the instrument. That leads to inaccurate measurements. So 50 ohms isn't just a number. It's fundamental to getting the cleanest, most accurate signal for the instrument to analyze.
Okay. But the manual gives a really critical warning here. Do not overload the input. Big, bold letters, probably.
Always a crucial warning for sensitive inputs.
It emphasizes that the maximum allowed power or voltage levels are detailed in the separate specifications document. Exceeding them can lead to incorrect results, obviously, but much worse.
Stuff to you too. Permanent damage.
Exactly. Permanent damage to the instrument's sensitive internal components. which I imagine are incredibly expensive to repair.
Oh, absolutely. Overloading the input stage of a sensitive RF instrument can seriously compromise its accuracy forever or just destroy the input mixer, often one of the most costly parts to replace.
It also highlights the default setting of AC coupling for the RF input. It says this blocks any DC voltage coming in with the signal, which helps prevent damage.
That's a smart default engineering choice. AC coupling provides a built-in layer of protection for general use, blocking unwanted DC offsets without the user having to think about it constantly.
But DC coupling is available for specific measurements.
Yes, but it requires, as the manual says, manual protection from the user. You have to be absolutely sure you're not feeding in damaging DC voltages if you switch to DC coupling.
So more flexibility, but more responsibility.
Exactly. It reflects that trade-off between advanced measurement capability and automatic built-in protection. It puts the onus on the user to be careful and knowledgeable when using those specific advanced modes.
Okay, finally for the physical tour, a quick run-through of the rear panel connectors. This thing looks like a real hub of connectivity.
Usually tacked on the back, yeah.
It's got a removable hard disk.
Yeah.
AC power input, obviously. DisplayPort and DVI for those external monitors. LAN for network control. Multiple USB ports front and back, usually. Sync trigger I/O for synchronizing with other gear. An auxiliary port multi-purpose, probably. A GPIB interface for older control systems.
Ah, GPIB, the classic. Still hanging around.
An optional OCXO input-output that's a more precise reference oscillator, right?
Oven-controlled crystal oscillator, yeah.
Yeah.
Super stable.
Standard REF input-output for external reference frequencies. And a device ID label. Phew.
That sheer variety of connectors really speaks volumes about the instrument's versatility, doesn't it? And its intended role within complex test setups.
How so?
Well, it's designed not just to work alone on a bench. It's built to integrate seamlessly with other lab equipment, maybe older legacy systems via GPI, and definitely into modern automated test setups using LAN or USB. It's like the ultimate Swiss Army knife for connectivity in the test world.
And the removable hard disk.
Yeah.
What's the benefit there?
That's particularly interesting. Could be for data security, maybe in classified environments you remove the disk with the data, or just for easily transferring huge data sets without needing a network connection. Allows for easy data isolation or maybe even system upgrades without network hassles.
Makes sense. Okay, so once everything's hooked up, the display becomes your main window into the deep dive of your measurements.
Your mission control dashboard.
Exactly. The RN FSPN's display looks pretty comprehensive based on the manual. It's broken down into key areas. There's a toolbar at the top with general functions, channel tabs for switching between different measurements, a channel bar right below that showing the key settings for the current measurement.
Okay, quick status view.
Then the main result display area where your graphs and tables appear, a Winday title bar above each graph giving trace info, a status bar at the bottom for system messages, progress indicators,
Useful feedback.
an input field for typing values, a diagram footer with diagram-specific info, and finally, soft keys along the side or bottom, providing quick access to measurement functions relevant to what you're doing.
It sounds like a well-organized layout, providing all the critical info without being, hopefully, too overwhelming. That separation of areas helps manage the information density, lets you quickly focus on different aspects, settings, results, status. It's designed for efficiency so you don't get lost swimming in data.
And you can even customize the view. You can hide things like the status bar or the channel bar if you want to make the main measurement results area bigger. You do that via Setup Display displayed items.
Nice. More screen real estate for the important stuff.
There's also a multi-view tab mentioned, which sounds fascinating. It lets you see an overview of all the active measurement channels at a glance, each with its own little channel bar showing its status.
Ah, multi-view. That's a really powerful visualization tool, especially if you're running complex tests with multiple channels simultaneously.
Like comparing different measurements.
Exactly. It allows for quick comparisons, monitoring different parameters or results, without constantly having to click between different tabs. It really enhances your overall test efficiency and insight. It's almost like having multiple mini-monitors built right into the main interface.
And those channel bars have helpful little icons too, providing visual cues. A star icon apparently means the displayed trace doesn't match the current settings anymore. Maybe you froze a trace and then changed something.
Ah, okay. A stale trace indicator.
An exclamation mark warns you if there's an error or warning condition specific to that channel. Super useful, especially in that multi-view if you're watching several things at once.
Draws your eye right to the problem.
And there's a special icon that highlights the currently active channel when you're running an automatic measurement sequence, something they call the sequencer, which we'll get to later.
These visual indicators are incredibly helpful, aren't they? For quick problem spotting and status checks. They act as an immediate heads-up, guiding you to potential issues or deviations without needing to dig through menus or read status logs. It's all about providing instant operational feedback, stopping you from misinterpreting data or wasting time on a setup that's gone wrong.
The window title bar, above the actual graph, also displays crucial trace information. Things like, is trace smoothing active? Are spurs being removed? Is there a trace offset defined? Ensures you know exactly how the data you're seeing is being presented.
Full transparency good.
And marker information showing the X and Y values at specific points on the graph, their index number, and which trace they belong to, like M21 for marker 2 on trace 1. That's displayed either right on the diagram grid or in separate marker tables for more detailed analysis.
Markers are absolutely fundamental for pulling precise data points out of graphical displays. Lets you pinpoint specific values within your results. And seeing the smoothing and spur removal settings right there ensures you always know how the displayed data has been processed. That's vital for accurate interpretation, especially if you're making critical design decisions based on these numbers.
And for long measurements, like those cross-correlation ones, there's a green progress bar. It indicates the progress for half decades, apparently, with a lighter shade showing ongoing measurements.
Visual feedback on long processes.
You can even double-click it to define the cross-correlation factor, or right-click for a context menu. And crucial instrument status info is displayed prominently, too. Things like RF OVLD means RF overload. You need to reduce the input signal level.
Right, protect the input.
UNCL means uncalibrated. You need to perform a self-alignment, or maybe correction data is turned off, or even wrong FW indicating the wrong firmware is loaded and an update is needed.
These status messages are the instrument talking directly to you about critical operating conditions. They prevent you from misinterpreting results because the instrument wasn't calibrated or the input signal was too strong. They guide you to immediate corrective actions to maintain measurement integrity. That cross-correlation progress bar is especially valuable for those lengthy noise measurements, giving you a feel for completion time and showing how the statistical confidence of the results is building up over time.
The soft keys, the ones that give you access to measurement functions, they even have a thoughtful color coding system for their status. Orange means a dialog box related to that key is open. Blue means the function is active, or it's in a toggled on state. And gray means it's temporarily unavailable for some reason.
Nice. Subtle visual cues that instantly tell you the state of functions.
And for more advanced users, or maybe when operating remotely, right-clicking or tapping and holding on the touchscreen, an item in the diagram brings up context menus with relevant functions. This is especially useful if you've hidden the main soft keys to maximize the display area.
Context menus are great for efficiency.
Basic touchscreen gestures are also supported, giving you yet another way to interact.
The color-coded soft keys, the context menus, they really streamline the workflow. They give immediate visual feedback on the instrument's state and offer efficient shortcuts to related functions, reducing the need to navigate through complex menu trees. And adding touchscreen support just provides another layer of intuitive interaction, especially good for quick adjustments or maybe drawing a zoom box around an area of interest on the graph. It's all about optimizing how you interact based on your preference and what you're trying to do at that moment.
When it comes to actually entering data, the manual details the process for typing in alphanumeric stuff, spaces, correcting entries with backspace, confirming with enter, or pressing the rotary knob, or canceling with ESC. Standard stuff.
Yep, the basics of data entry.
But let's zoom in on a really fascinating aspect of the display organization. Something called the Smart Grid principle for the result display.
Smart Grid. Okay, sounds interesting. How does that work?
Well, this seems to be where the interface really shines for complex analysis. In the Smart Grid mode, each measurement you set up gets displayed in its own separate tab. Keeps your workspace tidy.
One measurement per tab? Makes sense.
Now, while the instrument itself can only perform one core measurement at a time, that sequencer function we mentioned earlier allows you to configure multiple measurements to run consecutively, and the results update in their respective tabs as each measurement completes.
So the sequencer feeds into the Smart Grid tabs. Got it.
The Smart Grid view also features an evaluation bar. This has icons for all the available analysis methods or display types for the measurement you've currently selected.
Okay, like different ways to view the same data.
Exactly. And here's a key part of the Smart Grid experience.
Yeah.
You add new analysis windows, like a graph, a table, whatever, by simply dragging an icon from that evaluation bar onto the screen.
Drag and drop. Nice.
Yeah. And the position of the new window depends on where you drop the icon relative to the windows already there, so you can easily tile things horizontally or vertically. This drag and drop layout is apparently only possible in Smart Grid mode, which actually replaces the traditional soft key menu on the side. It seems like a significant shift in how you interact.
That drag and drop capability sounds incredibly intuitive. It lets you customize your display layout completely on the fly, doesn't it?
Seems like it.
It's a visual, direct manipulation interface. It simplifies arranging multiple data plots, tables, marker lists, tailoring the workspace precisely to what you need for that specific analysis. That feels like a huge improvement over rigid, predefined display layouts. It transforms the screen from just a static view into a really fluid, adaptive workspace you build yourself.
And once you have these windows open, you get full window management functions. You can close them, arrange them automatically, split the screen, maximize a window.
Standard window controls.
Yeah.
Good.
You can double tap a title bar to maximize or store, or use a dedicated split maximize key. They even have an option to display a virtual front panel or a smaller mini front panel right there on the screen.
Oh, like a software emulation of the physical controls.
Exactly. Which sounds super useful if you're using an external monitor or especially if you're controlling it remotely. It even comes with keyboard shortcuts that mirror the physical front panel keys.
Those on-screen soft front panels are brilliant, especially for remote operation. They replicate that tactile experience of using the physical instrument, but in a software environment.
Yeah.
Having that consistent interface, whether you're local or remote, it minimizes the learning curve and maximizes your efficiency. It ensures all those sophisticated capabilities remain accessible no matter how you're choosing to interact with it. It creates a really seamless user experience, whether you're standing right next to the device or controlling it from thousands of miles away.
All right, so we understand how to physically handle it, how to power it up safely, and how to navigate its pretty sophisticated interface, including that Smart Grid layout. Now, let's really dive into its core purpose, its fundamental measurement capabilities.
Okay, what can it actually measure?
A typical starting point for many users, according to the manual, is selecting the phase noise application. You do that using the Modo key.
Right. Selecting the mode immediately configures the instrument's internal signal paths, filters, processing units. Everything gets optimized specifically for that demanding task of measuring phase noise. It's like telling a high-performance card to switch into track mode.
Okay.
Everything inside reconfigures for maximum performance in that specific discipline.
And what's fascinating here, I thought, was the manual's acknowledgement that the firmware often provides multiple ways to change the same parameter.
Oh, yeah. Like what?
For example, you can define the measurement frequency range using the FREQ key, or a dedicated MEES config key, or through an overview dialog box. This kind of many ways to skin a cat philosophy. It suggests a really thoughtful design, doesn't it? Catering to different user preferences or workflows.
That flexibility is a massive benefit, especially for experienced users. Some people might prefer using the direct hard keys for speed, relying on muscle memory.
Right.
Others might prefer a graphical dialog box for a more visual, guided setup, especially if they're exploring a function for the first time. It caters to different operational styles, different levels of expertise. It lets you optimize your interaction based on your comfort level and how complex the task is. It really does imply a user-centric design approach, not just a rigid, this is the only way interface.
So let's get to the core. What exactly is phase noise measurement? The manual says it's the fundamental purpose of this instrument measuring the noise characteristics of a continuous wave signal, and it measures the combined noise characteristics of the components in the test setup.
Okay, phase noise. Think of it as the unwanted tiny wobble, or jitters, in what should be a perfectly stable, precise radio signal or clock signal.
A wobble.
Yeah, imagine a perfect clock ticking absolutely perfectly every second. Phase noise is like that clock sometimes ticking just a tiny fraction of a second early or a tiny bit late. It's instability in the timing or phase of the signal.
And why is that bad?
In high-tech systems, advanced communications like 5G or 6G, GPS navigation, sophisticated radar systems, high-speed data links, even a minuscule wobble can scramble data, lead to inaccurate positioning, or seriously degrade the overall system performance. This instrument's main job is to precisely measure that wobble, ensuring your signals are as clean and stable as possible. That is absolutely critical for modern technology to function correctly.
Okay, so that's phase noise. But beyond that, the RNS-FSPN also handles something called baseband noise measurements. What's that about?
Right, baseband noise. This is where it measures noise over an absolute frequency span, starting
Yeah.
from very low frequencies near DC up to maybe tens of megahertz. It's not relative to a main carrier signal like phase noise is.
And what's the use case for that?
This really expands the instrument's utility beyond just RF signals. Baseband noise measurements are crucial for characterizing the fundamental noise floor of components like, say, low-noise amplifiers or voltage regulators and power supplies, or DC voltage references.
Things that should be quiet.
Exactly. These are often the silent killers of system performance. They introduce unwanted interference or instability that might not be immediately obvious but can subtly degrade how the whole system works.
Yeah.
Measuring their noise directly gives you critical insight into their quality and how they might impact everything else down the line.
The manual mentions applications like checking the voltage supply noise of DC sources or determining amplifier noise characteristics, and the frequency range is incredibly wide, between 0 Hz and 30 megahertz in absolute terms. It says the dedicated baseband input extends the lower frequency range down to a remarkable 1 millihertz, whereas the main RF input's lowest frequency is 1 megahertz.
Wow, 1 millihertz. That capability is incredibly important for characterizing very low-frequency noise phenomena, things like flicker noise or 1F noise, which you find in active devices and power supplies.
Why is that important?
This type of noise is pervasive, and it can significantly impact the long-term stability and accuracy of sensitive systems. Being able to measure accurately down to such low frequencies gives you a really complete picture of the noise spectrum. That's vital if you're designing highly stable, low-noise systems, or just trying to understand the fundamental limitations of the components you're using.
But there's a critical note here, echoing the RF input discussion. The baseband input is always DC coupled.
Ah, okay. No AC coupling option there.
Right, which means the user must manually protect the instrument from potentially damaging DC input voltages. It's a powerful capability, measuring down to near DC, but it comes with a significant user responsibility.
That's a classic engineering trade-off, isn't it? Yeah. DC coupling is absolutely necessary to measure noise down to 0 frequency, which you need for characterizing certain types of baseband noise properly.
All right.
But it removes that inherent DC blocking protection you get with AC coupling. The manual explicitly states this, putting the onus squarely on you, the user, to make sure the input voltage levels are safe, to prevent damaging the sensitive internal circuitry. It's another reminder. Advanced functionality often requires heightened user awareness and very careful setup procedures.
Okay, so you've performed a measurement, either phase noise or baseband noise. The RNS-FSPN provides some robust features for refining and analyzing those results. One common technique mentioned is trace smoothing.
Averaging.
This averages the measurement data over multiple iterations or sweeps to yield a smoother, less noisy-looking trace. The application measures the data multiple times and then averages the results together.
Trace smoothing is basically a statistical technique. It improves the signal-to-noise ratio of your measurement visually. By averaging multiple readings, you reduce those random fluctuations, allowing the underlying signal shape and the true noise floor to become clearer.
So you can see the real trend better.
Exactly. It's about getting a more representative picture of the data by mitigating the impact of momentary variations, or maybe even the instrument's own internal noise contribution. It makes subtle details in the spectrum more visible and more reliable.
Then there's something called spur removal, spurs being...
Unwanted signals, spikes.
Right. This feature gives you the ability to effectively filter out these unwanted signals, or spurs, from the main trace display by setting a threshold level. Signals below the threshold are still shown, but anything above it can be excluded from the main trace visualization.
Okay, so it cleans up the view.
Yeah, but it's important to note the threshold you set is always considered in a separate spur table, whether the actual removal from the graph is turned on or off.
Ah, that's good. So spurs are typically these unwanted discrete frequency signals that can obscure the true noise floor or the measurement you're actually interested in. They might be harmonics generated by your device, or intermodulation products, or maybe just interference picked up from other equipment nearby.
Right.
Spur removal helps you isolate the noise contribution you are interested in, giving you a cleaner analysis of the continuous noise spectrum. But the fact that they're still tracked in that separate table is crucial for complete data analysis. You're not permanently deleting the information. You're just refining the visualization to focus on specific aspects of the signal. Still got the raw data on those spurs if you need it.
The instrument also provides integrated measurements. These summarize the residual effects like FM, frequency modulation, AM, amplitude modulation, and importantly, jitter into a results table. You can define up to 4 integration intervals or bandwidths.
Okay, summarizing noise over a band.
Residual FM is given in hertz, AM is in percentage, and jitter is in seconds. Importantly, for baseband noise measurements, these values are always 0, confirming they relate to noise around a carrier signal.
These integrated measurements provide a single summary metric of the overall noise performance within a specific bandwidth you care about. For example, residual FM tells you how much a signal's frequency is being inadvertently modulated by noise, critical for fidelity in communication systems.
And jitter, what is that exactly?
Jitter, in simple terms, is like the unsteady beat in a song. Instead of a perfectly consistent rhythm, the beats, or in the electronics world, the timing of electrical signal edges are slightly off. They arrive a little early or a little late.
Timing uncertainty.
Exactly. This timing uncertainty is a critical issue in digital systems. Even tiny variations in timing can lead to errors when sampling data or when transmitting data between components. It can cause data corruption, bit errors, even system crashes in high-speed systems. So measuring jitter directly tells engineers how noisy or unreliable the timing of their signals truly is.
Okay. The manual also mentions a spur list and jitter analysis feature. This displays detailed information on any detected spurs, including their absolute frequency, if you're doing baseband noise, their power level, and their contribution to jitter.
Quantifying the spur impact.
Yes, and it even distinguishes between 2 types of jitter. Discrete jitter, which is the RMS average of the jitter caused by individual spurs.
Okay, jitter from specific problem signals.
And random jitter, which is the jitter contribution purely from the underlying phase noise floor, without the spurs. This sounds crucial for understanding the real source of timing instability.
That distinction is quite sophisticated and incredibly valuable for engineers troubleshooting timing problems. Discrete jitter points to specific, often identifiable interferers or maybe poorly performing system components that are causing deterministic timing errors problems you can often track down and fix. Random jitter, on the other hand, is more like the fundamental inherent noise floor of the system's timing. You can minimize it, but never completely eliminate it. By separating these two, engineers can better diagnose and mitigate timing issues. They can tackle the deterministic problems caused by spurs first, and then optimize the design to minimize the fundamental random jitter. It really helps guide troubleshooting efforts efficiently.
There's also a spot noise feature. This lets you measure the noise level at specific individual frequency offsets from the carrier, these spots.
Like putting down specific measurement points.
Yeah, the results are displayed in a table. It includes predefined 10x frequencies like 1 kilohertz, 10 kilohertz, 100 kilohertz, and also lets you define up to 6 custom frequencies yourself. It's like placing a fixed marker at precise points of interest within your noise spectrum, giving you quick, targeted readings at frequencies that matter most for your application.
Spot noise measurements provide that quick, granular look at noise performance right at specific offset frequencies that might be particularly critical for a given application or standard. It complements the overall noise spectrum graph by giving you hard numbers at key points. It's a targeted analysis, very useful for verifying performance against specific design requirements.
Now, one of the most insightful visual cues on the display sounds like the cross-correlation gain indicator. This is shown as a gray shaded area on the noise spectrum graph itself.
Okay, a shaded region, what does it mean?
If your measured noise trace lies on this gray indicator, it means that performing further cross-correlation operations, basically, more averaging between internal channels, will still reduce the measured phase noise value, meaning your measurement could potentially get more accurate with more averaging time.
So it shows that there's still room for improvement.
Exactly. However, if there is a significant gap, a distance, between your measured trace and that gray area, it means further correlation will only smooth the trace visually. It won't actually reduce the underlying phase noise value any further. You basically hit the limit of what cross-correlation can do for that signal.
So it tells you when more averaging is just wasting time.
Pretty much. And there's even an optimized X-Core feature that can automatically stop the measurement when this gap between the trace and the indicator exceeds a certain threshold, like 10 dB, saving you unnecessary measurement time.
That gray area is a direct visual representation of measurement confidence and efficiency. It's brilliant. Imagine you're trying to hear a very faint whisper in a noisy room. Cross-correlation is kind of like having a second microphone. And by comparing the signals from both, you can filter out the background noise that's common to both, isolating just the whisper you want to hear. This indicator tells you, when you've done enough averaging, enough listening, that doing more won't actually make the whisper any clearer. It'll just smooth out the already accurate sound wave you've captured. It's a really clever way to save potentially significant measurement time and computational effort, ensuring you get accurate data without excessive, unnecessary processing. Very smart.
Finally, in this section, we have Allen variance and Allen deviation. These are apparently derived directly from the phase noise measurement results and are key indicators of frequency stability over time.
Allen variance, the gold standard for stability.
For you, the user, low values for both variance and deviation indicate a highly stable device under test, like a stable oscillator. High values point to instability.
Allen variance might sound a bit intimidating, but it's essentially the way to quantify how steady a clock signal or a frequency source is over different time intervals. Imagine trying to keep a perfect rhythm going for minutes, hours, days. Allen variance tells you how much that rhythm drifts or wavers over those different timescales.
So stability over time.
Exactly. A low Allen variance means your device is a rock-solid timekeeper. That's crucial for things like GPS accuracy, ensuring global communication networks stay perfectly synchronized, or for enabling high-precision scientific experiments that rely on stable timing. The curve usually shows a minimum point that marks the observation time where the frequency deviation is lowest. After that point, stability often deteriorates due to longer-term effects like temperature drift or component aging.
And what's really insightful, the manual says, is that the slope of the Allen variance curve on a log-log plot can help you identify the specific types of noise that are dominating the instability at different time intervals.
Noise identification.
Yeah, things like white phase noise, flicker phase noise, white frequency noise, flicker frequency noise, or even random walk frequency noise. Each has a characteristic slope.
That's incredibly powerful for diagnostics. Knowing the dominant noise type points you towards the likely physical mechanisms causing the instability in your device, guiding your efforts to improve it.
And the manual doesn't just leave you hanging there. It references a dedicated resource, Application Note 1EF69, Time Domain Oscillator Stability Measurement Allen Variance, for a comprehensive discussion.
Perfect.
This really highlights the interconnectedness, doesn't it? The user manual links out to deeper learning resources, guiding the curious user to truly master the underlying concepts and potentially become an expert in frequency stability analysis.
That's a perfect example of a comprehensive documentation ecosystem. The manual gives you the practical how-to, but then points you towards the deeper why and what else for critical, complex concepts like Allen variance. It supports your journey from just being an operator to becoming a true expert. It connects the practical application with the underlying theory. That kind of cross-referencing is really the hallmark of robust technical documentation, ensuring you can always dig deeper into the science behind the measurements if you want to.
Okay, so we've seen the intricate ways you can interact with the RNS FSPN manually, tweak settings, analyze results with markers, smoothing, Allen variance, all that good stuff.
Powerful manual operation.
But what if you need to run not just one measurement, but hundreds or even thousands? Maybe you're characterizing a big batch of new components or running long-term drift tests over days or weeks.
Yeah, manual operation becomes impractical very quickly.
Exactly. That's where automation comes in. And the manual introduces a powerful feature specifically for this called the sequencer.
The sequencer, okay.
The problem it solves is simple. Since the instrument's core hardware can only perform one measurement at a time, the sequencer allows you to set up a series of different configured measurements to run automatically, one after the other, consecutively.
So it automates running multiple different test configurations.
Precisely. This sounds like a critical feature for boosting throughput and efficiency in any kind of test environment, right?
Oh, absolutely. Instead of you manually setting up test A, running it, waiting, saving results, setting up test B, running it, waiting, you program the whole sequence once.
And let it run.
Exactly. It frees up valuable operator time. It allows for unattended operation run tests overnight, over the weekend, and it significantly reduces the chance of human error by ensuring you have consistent, repeatable test procedures every single time. It's automation at the task level, basically orchestrating multiple discrete measurements into a seamless, hands-free workflow.
The sequencer offers 3 different modes, giving some flexibility. There's single sequence, where each measurement in your list is performed just once, ideal for, say, characterizing one specific device.
Okay, run through the list once.
Then there's continuous sequence, which runs all the measurements in the list repeatedly in order. This is the default mode, apparently. Perfect for long-term monitoring or maybe burn-in testing.
Looping the sequence.
Got it. And finally, there's something called channel-defined sequence. This one first performs a single sequence run, but then it only repeats the measurements channels that you've specifically set to continuous sweep mode. A bit more complex, maybe for mixed testing scenarios.
Okay, some flexibility there depending on the test goal. And how do you know which measurement is running?
Remember that special icon in the tab label we talked about earlier? That indicates the currently active measurement within the sequence. And the results get updated in the respective tabs in the smart grid as each measurement in the sequence completes.
Right, so the different modes cater for various test scenarios, from one-off checks to continuous monitoring. And that active measurement indicator is a simple but really effective visual cue. It tells you exactly which test is running right now within your automated sequence without you having to guess. That kind of real-time feedback is essential when you're monitoring long-running automated tests. Gives you immediate insight into the progress and status.
Now let's talk about the real power of automation, remote control. This brings up an important question. Why would you want to control the sophisticated instrument from a distance instead of just using it manually right there on the bench?
That's a good question. There are several really compelling reasons. First, just pure efficiency. You can integrate the FSPN into a larger automated test system, right? Let a central computer control multiple instruments all at once, collect the data, process it in real time.
Okay, system integration.
Second, safety. What if your test environment involves high power levels or dangerous voltages, or maybe it's inside a shielded enclosure with potentially harmful electromagnetic fields? Remote operation keeps the personnel safe, away from hazardous conditions.
Right, makes sense.
Third, just the automation itself. Enabling unattended operation for those really long duration tests, drift testing over days, maybe environmental testing, frees up skilled engineers to focus on analyzing results rather than just babysitting the equipment and manually clicking buttons.
Saves time and boredom.
Exactly. And finally, integration again, but in a different sense. It allows the FSPN to become a precise component in really complex multi-instrument test setups, where data from different sources may be a signal generator, a network analyzer. The FSPN needs to be precisely synchronized and processed together centrally to figure out the overall system performance.
Okay, lots of good reasons. So how do you actually do it? The RNS FSPN offers several remote control methods. You can use the familiar Windows remote desktop application connecting over the LAN, which sounds incredibly powerful.
Yeah, full graphical remote access.
Or you can connect a controlling PC via the traditional GPI interface, that old parallel bus.
Good old GPI.
Yeah.
Still widely used in test and measurement.
And the manual also highlights vendor support here, mentioning that Rohde & Schwarz provides an auxiliary remote control tool called IECWN, apparently free of charge.
Now, that vendor support is significant. Providing a free, dedicated tool like IECWN really lowers the barrier to entry for automation, doesn't it?
Absolutely.
It makes it easier for users to get started with remote control, maybe write simple test scripts, without having to immediately buy expensive third-party software licenses. It shows a commitment from the manufacturer to empowering users to maximize the instrument's capabilities beyond just manual operation. It encourages them to leverage automation for greater efficiency.
And with that remote desktop connection, you get truly comprehensive access, it seems. The manual says it allows you to access all applications, files, and network resources of the instrument right from your remote computer.
Yeah, it's essentially like you're sitting directly in front of the instrument, but you're using your own keyboard, mouse, and monitor.
So you see the full graphical interface.
Exactly. Full graphical interaction, file system management. It's more than just sending text commands back and forth. You can see the display update, open other applications on the instrument, manage data files, just as if you were physically there. That's invaluable for debugging complex remote test setups and visualizing results in real time without needing to be physically present in the lab.
Now, here's something truly fascinating about the FSPN's remote capabilities related to that GPIB port. It's GPIB languages and emulation features.
Ah, emulation. That can be really useful.
The instrument supports a subset of the GPIB commands used by other, often older, devices. This allows it to effectively emulate them. The manual lists examples like the classic HP Agilent 711-100C spectrum analyzer, the 8560E, 8566AB, 8594E, and even the PSA or 89600 VSA series.
Wow, that emulation capability is a massive advantage for labs that have existing, maybe legacy, automated test setups or control programs.
Why is that such a big deal?
It means if you've already invested significant time and money developing software to control one of those older instruments, you might be able to use that same software, maybe to minimal changes, to control this brand new, much more capable RNS FSPN.
So you don't have to rewrite everything from scratch.
Exactly. This backward compatibility extends the useful life of your existing automation infrastructure. It saves potentially huge amounts of development time and cost. It's a really thoughtful design feature for customers who might be upgrading specific instruments within an established working test environment. It effectively bridges the past and the present of test and measurement automation.
The manual then dives into something called the SCPI recorder, which sounds like a crucial, almost magical tool for helping you automate your workflow.
SCPI recordings.
Okay.
Yeah, SCPI being the standard commands for programmable instruments.
Right. A key feature is called Show SCPI command. When you interact with the instrument, manually clicking buttons, changing settings, you can have it display the corresponding SCPI command that achieves the same thing programmatically.
Oh, that's brilliant.
This sounds invaluable for learning the programming language needed for automation, doesn't it?
It's essentially a built-in tutor for automation. It completely demystifies the programming process. It shows you the exact commands that correspond to the manual actions you're already familiar with. This dramatically shortens the learning curve if you need to develop automated test scripts.
Yeah, instead of digging through a dense programming manual for every command.
Right. You just perform the action on the instrument's front panel or GUI, and you see the required code snippet generated in real time.
Yeah.
That is genuinely a game changer for anyone starting out with instrument automation or even experienced programmers trying to control a new device.
And the SCPI recorder takes it a step further. It can automatically record a whole sequence of commands and their parameter values as you perform manual action.
Okay, so it logs everything you do.
Yes. And then these recorded command sequences can be exported directly into files formatted for common programming languages like C#, C++A, and even MATLAB, specifically for its instrument control toolbox. This massively streamlines the process of writing automated test scripts. You could, for instance, manually set up a really complex measurement configuration, record all the steps involved, and then export that entire sequence directly into your Python or C# or MATLAB automation script in minutes.
That is truly powerful. The SCPI recorder literally transforms your manual operations into ready-to-use code snippets. For engineers developing automated test sequences, this means drastically reduced development time and likely fewer errors because you're starting with proven working code generated by the instrument itself.
Yeah.
You perform the complex setup manually, record it, export it, and then integrate that code directly into your larger automation framework. It allows you to move incredibly quickly from just having an idea for a test to actually having it running automatically. It really accelerates development cycles.
And for when things inevitably go wrong with those automation scripts, the RNS FSPN also offers I/O logging.
Ah, debugging tools.
This feature gives you the ability to log all the remote control commands sent to the instrument, and often its responses too, into a file, usually called something like CAPI-log.number. This sounds crucial for hunting down misspelled keywords, syntax errors, or logic bugs in your control programs. It's like having a detailed diary of every command that crossed the wire.
Debugging is often the most time-consuming part of developing automation software, especially when you're interacting with external hardware. Having a comprehensive I/O log provides a detailed trace of exactly what commands were sent, in what order, and what the instrument's response was. It makes it so much easier to pinpoint where a remote control program might be failing, maybe incorrect syntax, maybe the instrument was in an unexpected state, maybe a timing issue. It's an absolutely indispensable tool for ensuring your automation is robust and for minimizing downtime when problems occur.
And if an error does occur during remote operation, the FSPN can be configured to display a message box right on its screen showing the error type and the specific offending command that caused it. Gives you immediate feedback.
Instant alert. Good.
All remote errors are also listed systematically in a dedicated tab within the Network Plus Remote Configuration dialog box, so you have a complete history log of any issues encountered during remote sessions.
Excellent. Having both the immediate on-screen alert and the persistent log is great.
Finally, there's a local soft key mentioned. This allows a user at the instrument's front panel to switch control back from remote mode to manual operation.
Taking control back locally. Important.
What's more, the instrument can even be configured to generate a service request, an SRQ signal over GPI, or an equivalent over LAN to actively inform the controlling software that the user at the front panel wants to regain manual control. This sounds like really robust human-machine interaction design.
That SRQ functionality is a prime example of really thoughtful HMI design, isn't it? It allows for a graceful interruption of potentially long-running automated tests. It gives the human operator control when they need it, maybe to investigate something unexpected, but it also intelligently communicates that intent back to the controlling software. This ensures a smooth, managed handoff between the automated process and manual intervention, rather than just abruptly cutting the connection. This layered approach to control, feedback, and error handling truly empowers the user in complex automated environments.
Okay, so you've successfully unpacked it, powered up safely, mastered its interface, maybe even that cool smart grid, and you've leveraged its powerful measurement and automation features, perhaps using the SCPI recorder. Fantastic.
You're an FSPN power user now.
Right. But what about keeping this high-tech workhorse running smoothly for years to come? This final section of the manual covers the essentials: maintenance, troubleshooting, and it even hints at the instrument's full life cycle.
Keeping the investment healthy. Important stuff.
Interestingly, unlike some complex machinery that needs constant tinkering, the manual states the RNS FSPN does not require regular maintenance, only occasional cleaning.
That's actually a testament to its robust design, isn't it? And probably the quality of the internal components. It suggests it's built for long-term reliability in demanding lab environments without needing constant intervention or scheduled servicing.
When it comes to that occasional cleaning, the manual is very specific, and it sounds like it's for good reason. Use no liquids, no solvents, no acids, no bases on the front panel, the plastic parts, or especially the display.
That's a standard but critical warning for sensitive electronics. Many common cleaning products contain chemicals that can degrade plastics over time, damage the anti-glare coatings often found on displays, or even seep inside the casing and cause corrosion or electrical shorts.
So just dust it.
Pretty much. Dry cleaning methods are almost always preferred. Maybe using compressed air carefully to blow dust out of ventilation openings, or just a soft, dry, lint-free cloth for wiping surfaces. You want to avoid any chemical corrosion or residue buildup that could potentially compromise performance or just make it look bad.
For storage, whether that's just overnight or maybe putting it away long term, you need to protect the product against dust accumulation and ensure that the environmental conditions like temperature and humidity stay within the specifications outlined in the broader documentation set. This is important even when the instrument is switched off and seemingly inactive.
Proper storage environments are absolutely crucial for the long-term health and, importantly, the calibration stability of precision electronics, especially those with sensitive components or mechanical parts like internal cooling fans, or maybe even spinning hard drives if it has one.
Why is dust bad when it's off?
Dust can accumulate inside, and then when you eventually power it on, it can act as an insulator, leading to localized hotspots. Or, if it gets humid, dust can absorb moisture and become slightly conductive, potentially causing shorts. And extreme temperatures or high humidity during storage can accelerate component aging, cause materials to degrade, or even lead to condensation forming inside, causing internal corrosion, all of which can compromise the instrument's accuracy and shorten its lifespan.
Okay, so keep it clean and dry, even in storage. Now, a really vital aspect of maintaining measurement accuracy day to day is performing a self-alignment.
Ah, yes, calibration's cousin.
The manual says this procedure is absolutely crucial for getting accurate results, especially for an instrument measuring down to the incredible precision needed for phase noise. The instrument is even smart enough to show a helpful reminder in the status bar if its internal temperature changes by more than 10 degrees Celsius compared to when the last self-alignment was performed.
That self-alignment process is key. It internally compensates for those tiny drifts and component characteristics that inevitably happen due to temperature variations or just the subtle aging of electronics over time.
Why is it so sensitive?
Precision measurements, especially things like phase noise, are highly sensitive to these minute changes. So the instrument actively monitors its own internal temperature and prompts you to run the self-alignment when needed. It's essentially a built-in quality control mechanism. It ensures your measurements remain accurate and trustworthy over time, even as the lab's ambient temperature might fluctuate throughout the day. Critical for scientific validity and ensuring your results are repeatable.
And there's a crucial precaution mentioned here. You absolutely must not have any signal connected to the RF input while the self-alignment is running.
Right. Disconnect the DUT.
Why, yes. It says it can lead to false measurement results.
Because during self-alignment, the instrument is measuring and characterizing its own internal signal paths and components. It's trying to calibrate itself. Any external signal present during that process would interfere, basically getting mixed in with the internal calibration signals. This would lead to incorrect correction factors being calculated and stored.
Ah, so future measurements would be wrong.
Exactly. Inaccurate measurements. The manual also advises you to await warm-up operation before self-alignment. Let the instrument reach a stable operating temperature first. Equally important. Electronic components need time to stabilize thermally to achieve their optimal, predictable performance characteristics before you try to calibrate them based on those characteristics. Trying to calibrate a cold instrument that's still warming up is like trying to precisely tune a guitar while its strings are still stretching and settling. You just won't get an accurate, stable result.
Makes sense. The instrument can also perform a self-test. This runs a check on its internal modules to help identify any defective components. Sounds like a useful first step in troubleshooting if you suspect something's wrong internally. Built-in self-tests, BIS, are invaluable for quick diagnostics. They let you rapidly determine if a problem you're seeing is likely internal to the instrument itself, or maybe external in your test setup or the device you're testing. Saves a lot of valuable troubleshooting time by narrowing down the possibilities quickly.
For its timing reference, the RNS FSPN can use its standard internal 10 MHz crystal oscillator, or you could feed it a more stable external reference source, maybe 100 MHz or 1 GHz signal from a lab distribution system, connecting it via the RFF input or maybe the fancy trigger connectors.
Flexibility in reference sources.
Good. And there's that optional, even more precise OCXO, the oven-controlled crystal oscillator signal available. If installed, this replaces the standard internal reference for achieving the absolute highest level of frequency stability and long-term accuracy. That flexibility in reference frequency sources is critical for maintaining the highest accuracy, especially for demanding measurements. An internal crystal oscillator is usually pretty good, but locking the instrument to an external, even more stable reference, often a high-quality house reference standard that's common to an entire lab, can push the instrument's measurement performance to its absolute limits. This is particularly important for critical phase noise measurements, where the stability of the reference source directly impacts the measurement floor you can achieve.
Okay, so what happens when things inevitably do go wrong? You suspect a fault or you just need help. The manual provides clear guidance for troubleshooting and getting support.
Hopefully you don't need it often, but good to know it's there.
It guides you on how to collect important information before you contact support. Specifically, it tells you how to create a .zip file containing key diagnostic data, the device footprint, internal EEPROM data, and importantly, a screenshot of the screen showing the problem.
Ah, packaging up the evidence.
Yeah, this is apparently crucial for enabling faster problem identification by the Rohde & Schwarz support team.
That standardized information package is absolutely vital for efficient technical support. It gives the manufacturer's engineers a comprehensive snapshot of the instrument's current state, its hardware configuration, maybe internal error logs stored in the EEPROM, and the visual context of the issue from the screenshot. It allows them to diagnose problems much more quickly and effectively, hopefully without days of back-and-forth emails asking basic questions. It's really about empowering the support team to help you get back up and running as fast as possible.
For even deeper diagnostics, if needed, you can apparently access the standard Windows event log files directly on the instrument itself, just like on a regular PC.
Leveraging the underlying OS capabilities, useful for advanced troubleshooting.
And when it comes to certain low-level service functions, things maybe only a technician should touch. Accessing them requires administrator rights on the instrument and sometimes special service passwords. The manual explicitly warns that incorrect use of these functions can affect correct operation and/or data integrity of the FSPN.
That multi-layered security for service functions is really important. It protects the fundamental integrity of the instrument's core functionality and its critical calibration data. By requiring admin privileges and maybe even hidden service passwords, The manufacturer ensures that only properly trained or authorized personnel can access and modify settings that could otherwise potentially compromise the instrument's performance, corrupt valuable measurement data, or even brick the device if done incorrectly. It prevents accidental or malicious tampering with the instrument's fundamental operation, safeguarding its scientific integrity and your investment.
Finally, the manual briefly touches on the end of the road, the life cycle of this high-tech tool, covering transporting and disposal.
The beginning and the end.
It reiterates those lifting and carrying safety precautions we discussed right at the start. It emphasizes, again, using the original packaging for transport, as it provides the best protection, and ensuring the instrument is properly secured in vehicles to prevent damage during transit.
That emphasis on using the original packaging for transport is very practical advice. That packaging isn't just a cardboard box. It's usually custom designed with specific foam inserts to protect the instrument from the particular shocks and vibrations it's likely to encounter during shipping. A generic box just wouldn't offer the same level of protection.
And the brief mention of disposal, it just serves as a reminder, doesn't it? That even these complex, expensive instruments, like all technological products, eventually reach an end of life. And responsible disposal, following local regulations for electronic waste, is something users need to consider for environmental stewardship.
Absolutely. While disposal is just a brief note, it speaks to that broader concept of product stewardship. It acknowledges that even sophisticated electronics eventually become obsolete or fail, and they should be handled responsibly at the end of their useful life, especially given the specialized materials and components they contain.
Wow. Okay. We started this deep dive with what might seem like a pretty mundane document, a user manual for the RNS FSPN from Rohde & Schwarz.
Yeah, not usually bedtime reading.
No. But what we actually found was this incredible wealth of information, way beyond just simple instructions. We uncovered critical safety protocols that really speak to meticulous engineering. We discovered thoughtful philosophies about user-friendliness embedded in its interface design, like that smart grid. We explored its incredible precision measurement capabilities for things like phase noise and frequency stability using Allen variants. And we delved into those really advanced automation features like the sequencer and that amazing SCPI recorder tool.
It's true. We've seen how a top-tier manufacturer like Rohde & Schwarz really considers everything, from the physical environmental conditions needed for optimal performance, all the way to software compatibility features like emulation, which allow a brand new instrument to integrate with test systems that might be decades old.
Yeah.
And they even provide tools like that SCPI recorder designed specifically to help you, the user, become a power user through automation, literally generating programming code from your manual actions. It's a really holistic approach, isn't it? Engineering not just a device, but an entire ecosystem for using that device effectively.
It really feels like a roadmap, not just for operating the specific instrument, but for truly leveraging any complex piece of engineering. It's a testament, I think, to how detailed documentation and really thoughtful design can transform what looks like a daunting piece of technology into an accessible, powerful tool, ready to tackle the most demanding scientific and engineering challenges out there.
Absolutely. The level of detail, those explicit warnings, the transparent explanations of why certain steps or precautions are necessary, and then coupling that with innovative tools for automation, it all reflects a profound understanding of the user's journey, right from that initial unboxing excitement through advanced application development and all the way to long-term maintenance and support. It really encourages a shift in perspective, doesn't it? Moving from just being a consumer of technology to truly understanding and mastering it.
So the final question then. What does all this mean for you listening right now? Consider how this level of detailed documentation, this transparency, these built-in automation features, how might that change the way we approach any complex system? Not just scientific instruments, but maybe even the increasingly complex everyday appliances in our homes.
That's an interesting thought.
Could more everyday technology benefit from such a transparent and robust approach? To user information, to control, giving us, the users, more power and more insight into how our tools actually work and how we can get the most out of them. What seemingly simple manuals or interfaces in your own life might hold the key to a deeper understanding if only you took the time for, well, a deep dive.
Something to think about,
We'll
definitely.
leave you with that thought.